While a sine wave may appear as a smooth and continuous curve, it is actually constructed from an infinite series of discrete segments, each characterized by its own slope. These individual segments collectively give rise to the characteristic oscillating pattern of the waveform. Any amplification or attenuation of the sine wave results in a modification of all the slopes within each segment. Sine wave amplification or attenuation are very difficult to perceive visually. Despite being difficult to perceive visually, this affects every slope uniformly. Therefore, analysis typically focuses on the percentage change applied to a single slope, as this change propagates along the signal path, influencing the entire waveform. By examining the inflection or deflection of the signal along its path, engineers can determine the impact of geometric alterations on field flow. This analytical approach transcends frequency and signal level considerations, with the primary parameters of interest being the maximum drive slope and the signal period. When comparing the slope or rise over run of the red drive signal with that of the blue input device, we observe a divergence that results in the derivation of the green 0.6 line. This deflection signifies the impact of trace impedance to load mismatch. As a signal propagates through a circuit board, it often encounters multiple geometry changes along its path, leading to the occurrence of multiple inflections. By comparing the slope of the signal at various points along its path to the slope of the input signal, insights into the nature of these geometry changes can be gained. In the context of this example, the amount of inflection change exhibited by the violet line is illustrated by the orange line. This comparison allows engineers to identify and understand how alterations in the geometry of the signal path influence signal behavior. Good luck using S parameters to determine how to adjust the printed circuit board for better performance. TDR measurements are not too helpful either. The alteration in field flow can serve as a valuable indicator of changes in geometry along a signal path. For instance, comparing the slope of the violet line to that of the blue line allows for an assessment of the impedance difference between the transmission line terminating at point P4 and the load resistor. This technique provides insight into how variations in geometry impact signal impedance at different points along the path. While this slide demonstrates the concept using simple geometries, the methodology can be applied to more complex geometries as well. The methodology presented in the previous slide offers a versatile approach for calculating various geometries along a signal path. By analyzing the inflection at each point and comparing it to the preceding point, engineers can assess the impact of changes in geometries along the path. This technique allows for a detailed understanding of how alterations in circuit board layout and structure influence signal behavior and impedance. By systematically evaluating inflections, engineers can pinpoint areas where geometry changes may lead to signal degradation or interference, enabling them to make informed design decisions to optimize signal integrity and performance in electronic systems. The methodology described involves straightforward mathematical calculations, primarily division, without the need for complex operations such as phase shifts or calculating partial inductance. By simplifying the analysis to basic mathematical operations, engineers can efficiently assess signal behavior and impedance changes along a circuit board path. This simplified approach streamlines the analysis process, making it more accessible and practical for designers and engineers. It allows for a quick and intuitive understanding of how changes in geometries affect signal propagation without requiring advanced mathematical techniques. As a result, engineers can focus on optimizing circuit board layouts and structures to ensure optimal signal integrity and performance without being encumbered by intricate mathematical computations. In the world of super high-speed designs, the interface between the component and the printed circuit board poses one of the most critical challenges. Despite meticulous routing on the PCB, the effectiveness of the part-to-board interface can ultimately determine the success or failure of a design. This interface is inherently complex and often beyond the developer's full control, primarily due to the intricacies of the component's package. Unlike traditional circuit considerations centered on current flow, Achieving optimal performance in high-speed designs necessitates a paradigm shift towards understanding and facilitating the flow of electromagnetic fields. However, this shift in mindset can be challenging, even for the most credentialed, as it requires breaking away from conventional thinking patterns. In such designs, the flow of electromagnetic fields must traverse various interfaces, from decoupling capacitors to the die, through the pins, and onto the board, establishing crucial references along the way. Each interface must be meticulously engineered to facilitate this field flow effectively. Establishing the relationship between different references is paramount, ensuring seamless transmission and reception of signals across the entire circuit. The following sections of this document will delve into the fundamental principles governing the package-to-board interface, shedding light on strategies to optimize this critical aspect of high-speed electronic designs. In PCB development, unlike the external connections where we can exert some control, the internal reference within the device is typically beyond our influence. As a result, the primary task becomes controlling the relationship between the signal path and the leads along the trace on the PCB. This slide illustrates how effectively a signal propagates from the device down the trace in a typical layout scenario. In this configuration, the reference for the trace lies below the trace, with the pin containing the via serving as the reference net. It's essential to understand that even with precise layout planning, a signal's transition along the trace. For instance, a 1 picosecond source signal may take approximately 100 picoseconds to transition as it propagates down the trace, highlighting the intricate nature of signal propagation in super high-speed PCB designs. However, it's essential to distinguish this transition time from propagational delay. Propagational delay refers to the time it takes for a signal to travel from one point to another along a transmission line, and is influenced by various factors such as the dielectric constant of the substrate, trace length. In contrast, the transition time described here pertains to the time it takes for a signal to transition or change its state as it travels along the trace. When examining the deflection or change in slope along a trace from its source to a specific point, it becomes evident that only a fraction of the electromagnetic E field propagates down the trace. Despite the signal's initiation at the source, its journey along the trace is subject to various factors such as reference transitions, substrate properties, and trace geometry. Consequently, the distribution of the E field along the trace is non-uniform, with only a limited portion of the initial signal's energy effectively traveling down the trace. In this illustration, the propagation of a signal originating at port 1 along the trace and past port 2 and port 3 is depicted. However, the signal experiences significant attenuation and elongation of its period along this path. This degradation in signal quality is attributed to the reference transition occurring from the pin of the device to the reference plane situated beneath the trace. As a result of this transition, the signal transition time along the trace becomes longer than the original period of the signal. Consequently, the propagation of this transition only occurs for the duration of the signal's period. Given that the transition duration surpasses the period, only a fraction of the transition manages to propagate effectively, leading to severe signal attenuation. The period is based on the input, so a slower slope is attenuated over the same time period. In this case, it is 100 picoseconds. A fly-through of the cross-section along the propagation path will show the relationship between conductors separated by an insulator. The animation illustrates a notable disparity in the relationship strength between the part pads and along the trace. This variance in relationship strength induces a deflection in the transition time of the signal. Initially, the signal begins with a dominant reference laterally situated between the pads. However, as it progresses, the dominant reference undergoes a transition to the reference plane positioned beneath the trace. To ensure efficient field propagation, it becomes imperative to enhance this reference transition. Fortunately, this enhancement doesn't necessitate complex calculations, but rather relies on a straightforward understanding of applied field behavior. By addressing such reference transitions, engineers can effectively optimize signal integrity and minimize signal distortion in super high-speed PCB designs. By ensuring efficient propagation of field energy from the pin to the space between the signal pad and the reference plane, signal propagation can occur with minimal distortion. The animation illustrates the relationship between conductors separated by an insulator, focusing on a pad structure chosen for this specific application. This structure connects the return pin to the reference plane before reaching the connection point on the signal pad. This configuration allows the magnetic field to propagate tangentially to the signal propagation, optimizing signal integrity. While the animation excludes implementation specifics due to available technology, it serves as a demonstration rather than a rigid guideline. Its primary purpose is to illustrate the flow of electromagnetic fields. The encouraging aspect is that a 1 picosecond transition with a period of 20 picoseconds can effectively propagate within a well-designed printed circuit board. However, the challenge lies in the fact that many devices are not inherently designed to facilitate proper field flow. Often, device models are derived from measurements conducted on poorly laid out printed circuit board. This poses a significant hurdle during simulation, as it becomes difficult to discern whether issues stem from the board or the device itself. While this ambiguity may not be critical during validation, it holds significant importance in the realm of printed circuit board development. To address this challenge, engineers must focus on developing printed circuit boards capable of accommodating even the fastest signals. By prioritizing the enhancement of field flow within the printed circuit board design, engineers can ensure that the printed circuit board itself does not become the weakest link in signal propagation, thereby enhancing overall system performance and reliability. Transitions in field flow within a printed circuit board can lead to reflections caused by various scenarios such as device switching, device drive, device input, reference transitions, or conversion of field energy to heat. These transitions adhere to 3 broad categories: fixed energy, fixed voltage, and fixed current. When transitions in the field path occur from a weaker relationship to a stronger relationship or lower impedance, a drop in measured voltage and an increase in measured current are observed. Conversely, transitions from strong to weak relationships result in the opposite effect. In scenarios involving fixed voltage transitions, such as reflected waves returning to the drive, changes in voltage and current occur in the same direction. A reflection wave lower than the fixed voltage will elevate both the voltage to the drive and the current, contributing to the current supplied by the drive. Conversely, if the reflection wave exceeds the fixed voltage, the voltage decreases to the fixed level, and the current is subtracted from the drive's current. The behavior of fixed current transitions mirrors that of fixed voltage, albeit with reversed roles. Understanding and effectively managing these transition effects are crucial in optimizing signal integrity and minimizing signal distortion in super high-speed printed circuit board designs. By recognizing the impact of transitions on voltage and current levels, engineers can implement targeted strategies to mitigate reflections and ensure smooth signal propagation throughout the circuit. In a transmission line where the impedance is lower than the termination resistor, field energy propagates from the source towards the termination resistor. Upon reaching the termination resistor, the energy undergoes a transformation into heat. As a result, the termination resistor develops a voltage higher than that of the incoming wave, while the current through the resistor is lower than that of the transmission line. Subsequently, the stronger electric field and weaker magnetic field propagate back towards the source, representing a fixed energy reflection. As this reflection reaches the source, the voltage and electric field are compelled to match the source voltage, causing a proportional decrease in current. The weakened electric field and magnetic field then propagate towards the termination once again. Upon reaching the termination, the decrease in the electric field induces a drop in voltage across the resistor and an increase in current through the resistor. When the termination impedance exceeds that of the transmission line, Any change in the electric field is amplified, with the change in the magnetic field occurring in the opposite direction. In scenarios where the source voltage is fixed, any alteration in the incoming electric field strength corresponds to a change in the outgoing electric field strength and a corresponding change in the magnetic field in the same direction. These reflections continue to oscillate back and forth until the source voltage and current equal the termination voltage and current, ensuring signal equilibrium. In this visual representation, voltage and current measurements are depicted at three critical junctures along a trace: the drive, midpoint, and termination. Each specific time marker corresponds to the arrival or traversal of the evolving field wave along the trace. The red line and arrow signify the drive source, symbolizing the initial point of signal injection. The green line and arrow denote the midpoint of the trace, providing understanding into how the signal behaves as it traverses the trace. Finally, the blue line represents measurements taken at the termination resistor, offering valuable insights into signal termination and reflection effects. At T1, the commencement of the changing field wave propagation is signaled by the drive, adhering to Rule 1. The current dependency is dictated by the trace impedance. At T2, the changing field waves traverse past the midpoint. At T3, Rule 2 is invoked as the rate of incoming voltage change intensifies due to the elevated value of the termination resistor. Simultaneously, Rule 3 takes effect as the rate of current change dwindles owing to the higher termination resistor value. At T4, the changing field waves pass the midpoint originating from the termination resistor. Rule 1 comes into effect. At T5, Rule 4 becomes applicable as the voltage undergoes a transition to align with the drive voltage. This transition triggers a change in current, determined by the trace impedance. Concurrently, following Rule 5, the incoming change in the magnetic wave combines to generate a quicker rate of change. At T6, the changing field waves progress past the midpoint. At T7, Rule 2 is pertinent as the incoming rate of voltage change escalates due to the higher termination resistor value. Simultaneously, according to Rule 3, the rate of current change decreases owing to the higher termination resistor value. At T8, the changing field waves traverse past the midpoint originating from the termination resistor. Rule 1 is applicable. At each marked time interval on this slide, we observe voltage and current measurements taken at three significant points along a trace: the drive, midpoint, and termination. These distinct time markings symbolize the progression or traversal of the changing field wave along the trace. The red line and arrow signify the drive source, symbolizing where the signal is initially injected into the trace. Meanwhile, the green line and arrow denote the midpoint of the trace, offering valuable insights into how the signal behaves as it travels along the trace. Lastly, the blue line represents measurements taken at the termination resistor, which provide crucial data regarding signal termination and any reflection effects that may occur. At T1, Rule 1 is applicable as the propagation of the changing field wave is instigated by the drive. Furthermore, the current is contingent upon the impedance of the trace. At T2, the changing field waves traverse the midpoint. At T3, Rule 2 comes into effect as the incoming rate of voltage change decreases owing to the lower value of the termination resistor. Simultaneously, Rule 3 becomes relevant as the rate of current change increases due to the lower value of the termination resistor. At T4, the changing field waves cross the midpoint originating from the termination resistor. Rule 1 applies. At T5, Rule 4 is activated as the voltage undergoes a transition to match the drive voltage. Consequently, this voltage shift induces a change in current, which is influenced by the trace impedance. Simultaneously, in accordance with Rule 5, the incoming change in the magnetic wave combines to generate a faster rate of change. At T6, the changing field waves traverse the midpoint. At T7, Rule 2 is applicable as the lower value of the termination resistor leads to a decrease in the incoming rate of voltage change. Similarly, Rule 3 comes into effect as the lower value of the termination resistor results in an increase in the rate of current change. At T8, the changing field waves cross the midpoint originating from the termination resistor. Rule 1 applies.